So for those who joined a little late, let me quickly go over what we'll be covering today. We'll be doing the box culvert bridge modeling through MIDAS Civil, for which we'll be defining the material properties and everything else that includes node and element creation, um, boundary conditions assignment, static loads definition and assignment, and live loads generation, including four lanes as per ASH2 LRFT, and using HL93 truck vehicle will be done using box culvert wizard of MIDAS Civil, and then we'll move on to analysis and design. This is the plan of the bridge. The span is 42 feet and the transverse section is 66.2 feet wide. The bridge has a skew of 20 degrees, and if you look at the elevation, we have a wing wall of 26.3 feet width, and the depth of the bridge is 26.3 feet. So now let us quickly start with the modeling of this bridge. So I'll open the software, and this is how the blank MIDAS Civil window looks like, and I'll start by defining some material properties. So I'll just right click on the model view window, go to properties and select material, and the material I'll click add, and I'll select concrete material, and I'll select grade 4500 concrete and click apply. So in this way you can easily define the material properties. Then you can click close here. I'll switch to works tab and then go to model structure wizard and select reinforced concrete frame or box culvert wizard, and you'll see a dialog box open like this, where I'll switch to box culvert. You can choose what kind of structure you want to make. It can be a 2-dimensional, 3-dimensional analysis, it can be normal type frame, it can be pie type frame, as you can see the different layouts, or a box culvert. So from box culvert I'll select the material property that I defined for the bridge. I can give the dimensions of the plate element, and I forgot to mention that this bridge will be completely made of finite elements. That means it will have all members modeled using plates. The span length, if as you can see here, is 504, which is 42 feet. The thickness of the wing wall has been entered, the skew angle has been entered, and the dimensions, as you can read from the bitmap image given here, have been entered. So if you are modeling a box culvert with multiple voids, you can select span 1, span 2, span 3, and span 4 by entering the data in separated by comma. You can even include radius of curvature if it's not a straight bridge and it's along a curvature. Just click on radius. You can select convex or concave. You can select the layout of the bridge as well. But for this example, we'll stick to the default values here, and then move on to the Transverse Direction tab, where you can define the cross section of your bridge. You can define where your carriageway is, how much is your sidewalk, and where the barriers are located. And once you have entered those information, you can give the dimensions of your plate elements in the transverse direction, and you can have different layout of the bridge to choose from. Either it has barriers at both ends, it has a median and a barrier, it has a median at the other end and barrier at the right end. You can select to have springs to model the subgrade reaction, as you can see here. So modulus of subgrade reaction has been entered here, and the length of the elastic link has been entered here to transfer the shear effect. So I'll stick with these values and then move on to the loads tab, where you define the load combinations. So you can select the load combinations have to be modulus per AASHTO LRFT. You can select the moving load code to be as per AASHTO LRFT. You can click OK here. Then you can check on what all forces or loads you want to consider onto the structure. Self weight, pavement weight, you can enter the density of the pavement material. Soil weight, you can enter the density of the soil. You can enter the phi for the soil, that is the internal friction angle. You can enter the surcharge if any, and you can define the underground water level height from the ground, and you can tell what should be the submerged weight density of that soil. So the program will automatically switch the load from unsaturated to saturated soil pressure. You can consider barriers where they are located, what should be their self weight as applied onto the structure. If you want to consider additional loads, you can enter them right here. You can choose to have sidewalks, and since our model has that, we have entered this its weight density. You can also mention some crowd loading if you want to have in terms of pressure loads. You can specify the weight density and the thickness of the sidewalk that you want to use. So you can see how flexible this dialog box is to replicate the real world scenario. And with this kinds of inputs and just looking at your drawings, you can enter all these details and generate and very closely replicate your model or the real bridge in no time. You can check on live load and select you want to use what kind of vehicle and from which side of the edge of the bridge you want to define the eccentricity. Through this control you can generate loads onto the structure in no time. You can consider either 93 truck, tandem, or you can have both on them. You can have eccentricity from the left hand and the right hand. And once the model is generated, the beauty of this software is you can still go in and modify any details you want. It's not like other popular softwares where once the model has been generated, you cannot make any changes, and if you try to do that, everything is lost. You can choose to have a temperature gradient and a system temperature increment. We are choosing the temperature gradient to be as 5, delta T as 5 units of whatever unit system you are using for degree Celsius or Fahrenheit, and the difference of system temperature from 0 to what temperature you want to see. So that's been taken as 10. You can choose to have shrinkage, strain, and thermal coefficients that you want to apply onto the structure, and then you can either choose to save this as a wizard file for using it later on, or you can click OK to run this wizard file. So the reason you would like to save this wizard file is that when you want to create similar bridges again and again, let's say you have a library of bridges that you want to generate, then you can save these wizard files and then open it later on in a different model, make some changes here and there, and just hit OK and generate the bridge. So in this way you can just do all this hard work of entering the data set once, and then later on you can save time on every second bridge that you are making. So this adds to your productivity and increases your efficiency. Then you can click OK here, and as you can see, in no time the bridge is generated. It's a box culvert that you are looking at, and if I press down the control button from the keyboard and hold down my wheel mouse button, you can see the structure being rotated freely, and all the nodes that you are seeing are basically the finite element nodes meshing, and at the base we have the supports. You can choose to undisplay the nodes if you want to have a better view of your model. I click OK here, and now it's a lot clearer. If I go to the plan view, You can see the skew there. If I go to the front view and the side view, you can see the bridge. This is the wing walls that has been modeled, and here you can see all the loads that are applied onto the structure. So you can see the self weight and the pressure loading that is applied. You can just right click and display them onto the screen. You can select other loads that are there, and all the loads have been described here, that what do they represent in the reality. So you can see the DC, DW components onto the structure. You can choose different scale to see the values. Let's say kips per foot, or let's say pound per foot, and you can see the values written. If you find it hard to read this, as in this case, you can always choose to generate the table from it. You can right click, select tables, and you'll see all the loading in the tabular format in the given unit system of pounds per foot square. These tables are dynamic in nature. You can change the values here. It will be reflected in the model file. You can choose to see particular columns at a time and collapse the not needed ones. So that in the one display you can have the complete view of the loading. Also, you can choose to sort this dialog box. You can right click, go to sorting dialog. You can if you want to sort it based on load types or load case names, you can choose them and then click sort. Click close. So you can see all the loading with their values laid down as per load cases, making it much more readable. You can always right click and export this information. You can right click and export this information to a spreadsheet, or you can directly copy the entire thing by clicking on this button. You can copy and paste it into a spreadsheet to generate the replica of it. And if you have this information in spreadsheet, you can always copy and paste it in this table to generate the loading onto the structure. Let me quickly close this and come back to the model itself. Right click and select undisplay. Now let me show you some other loadings that are there, like the earth pressure. Right click and display. So you can see hydrostatic loading onto the structure as shown here, onto the wing walls and to the walls, and based on your water level conditions you can see all the loadings that are there. Let me just undisplay everything here, and let me show you the lanes. So I can just, you can see 4 traffic lanes have been generated based on the specific spacing given as per the codes. You can just right click and display them onto the screen. Let me go to the top view here, and you can see there are 4 lanes. I think this will be a better representation, and let me zoom in at this point. So you can see lane 4, lane 3, lane 2 and lane 1, and this side has been given for sidewalk and the barrier. So undisplay this. So, and also the program has generated the point springs at the required locations. So you can choose right click and display them onto the screen. You can see the point spring locations, and you can also see the fixed supports that are applied at the extreme ends. Let me go to the elevation. So this is the fixed support that have been applied, and the connection between the bottom of the bottom slab, and the soil has been replicated using elastic links. So you can just right click and display them onto the screen. And the properties of this elastic links have been entered as per the data available or provided into the wizard. So let me just go back here. And show you the wizard. So as you can see here, we entered some values right here. So this data goes into the program right here. Alright, so once this has been generated and everything is set for analysis, I'll just display them and quickly go ahead and perform the analysis by clicking on this button. I'll save this with some model file name. Let me say just some random name. Let's say I'll just save it with some random name. Let's say BC123. And now you can see the analysis being performed, and the message window you can see what steps are being performed right now. And just to remind you that the program is doing the live load analysis on the finite elements along with all the set of loadings that have been applied. And in less than 30 seconds, as you can see on the screen, the analysis is completed. So most of the time we being engineers shy away from finite element modeling because of three reasons. The first being modeling takes a lot of time, and second reason being the analysis takes longer, and the third reason being after the analysis we cannot extract the results that easily. So as you can see, the first point has been taken care of by the program by using a wizard and generating model in no time. The second point being analysis taking longer, so you can see it has a super fast engine and a multi-frontal sparse Gaussian solver that runs the analysis at lightning pace, and you can see within less than 30 seconds the analysis is completed. And the third portion is result extraction takes time, so let me quickly go over and cover that as well. So now I'll show you the program also generated the load combinations. So if I go to result combinations, you can see the load combinations are automatically generated by the program because we defined the load combinations as per AASHTO LRFT. So you can just click on the load combination and see the load cases that are there along with the load factors. So the solutions are basically the program is now set to extract the results. So I'll just click close here and quickly go through some basic checks. So right click and go into deformations, and I'll go to displacement contours, and then let's see how much the structure deflects under dead loads. I'll check on deform shape and the legend and then click apply. So here you can see the maximum deflection is occurring at the midpoint, and the units are given for deflection in foot. Let me change it to inches. So you can see it's about like 0.37 inch is the deflection occurring right at the top of the structure. But the geometry that you're seeing here is scaled up, so you can get it to be more realistic by reducing or controlling the deformation scale factors. So this is somewhat more realistic, although the value is less, but the program shows an exaggerated image for better comprehension. So this looks fine to me. Then I can move on. I can choose any load combination that I want. I can see the temperature gradient loading, let's say, or the system temperature, let's say, increased. So what is the effect of loading onto this? You can see the contours plot, You can choose that if you want to see the deformation only along x-axis, deformation only along y-axis, only along z-axis, and you can see the values right there. And as I mentioned, all these values can be exported into spreadsheet format. So you can just click on this button with 3 dots, select the load case that you want to see. Let's say dead load, let's say temperature gain. So click OK and you get the deformation in no time. Now you want to see where the maximum deformation is occurring. You can either just look at on your from your display, you can get it, or you can just sort this dialog table as well. Right click, sorting dialog. You want to sort based on DZ values. You can set the priority as top, click sort, and now you can see the one which has most deflection in the negative direction is at the top, and the one which has least will be at the bottom, along with the load case and the node number. So in this way you can easily interpret your results. Then let me go on to show you some force results. I'll switch to the force tab and select plate forces and moments. Then let me choose some simple load case right for the timing. Let's say static load as per dead loads. I'll choose to display average nodal. Basically each plate has got 4 nodes, and 4 nodes will have different values. So for generating a smoother contour, you can choose to have an average nodal value, so the program will average out the force values from those 4 nodes and display it, so you can see a smooth transition. And you can see you can choose different components of the force. So let's say mxx, which is equivalent to bending moment about major axis for our 1D elements. And then I'll check off deform shape and legend, and check on legend, and then click apply. So if you can see here, this is the loading value. Let me change the units to inch foot or foot kips. So now you are seeing the plate forces, and the units are foot kips per foot. So per unit length, you can see the display of the forces that are there, and you can very easily generate the plots also on the same contours. So for that we have a feature called cutting diagrams. I can check this on, and then the program will will bring up this small dialog box where I can cut across a plane. Let's say I want to have display of from this end to, let's say, this end. Click add here, and let's say I want to have a display of from this end to this end, and click add here, and then I'll click apply. So you can see here the program is showing you the graphs of the stresses, or the forces per unit length in this display. And if you are uncomfortable, or if you want to see it in the usual format as you anticipate them, so you can choose to reverse these graphs and then click apply. So now you can see them in the other format. And these lines need not be always orthogonal or straight. You can choose and cut across any along any axis and see the results. So if it's a skewed bridge and you want to see along the skew, you can choose to do that as well. And having done this, let me show you some live load results as well. So for the plate elements, so you can choose, let's say, MV max, which means maximum positive bending moment envelope, and click apply, and this is what the program is generated. So this is the live load envelope contour plot, and I can choose any element and generate the loading pattern for that same. So if I'm curious to know that what loading pattern cause maximum bending moment at this particular location, I can choose right click, go to moving load tracer, and select plate forces and moment, and then just click on that particular element which is of interest to me, element 161 in this case. So I'll click on this element. You can see the element number entered here. I can choose either I want to see it at the center or the four corners, I, J, K and L, going in the direction of the plate generation. So I, J, K and L. So let's say I want to see it at the Jth end. Again, I'm looking for MX6, and then I'll click on right maximum, and after that I also want to see the result, let's say at this particular element, which happens to be element number let me see, let's say I don't want to overlap and pick a wrong one. Let's say element number 154 for instance. So let me first generate the loading pattern that cause maximum bending moment at this element. I'll click apply, and the program will show me the loading pattern. So you can see that there are the 3 lanes are occupied, and the red flag that you can see here represents the axle or the wheel location. And if you want, I can switch the background to white or change the load display color. To let's say magenta, and click OK. So you can see the values of the red flags are the wheel locations, the blue color the blues represents the lane load onto the structure, and this is the vehicular location, vehicular load pattern that causes maximum bending moment at that particular location. And I can convert this loading into a static load case just by clicking on this button which says write min max to the load file, and then I'll click OK. And here you can see text file is created in no time. Let me just close it and investigate the next element that I wanted to see, which happened to be element number 156, or as a matter of fact I can pick any element I want, so let me just pick any one at some distance, let's say here, and then click apply. And this is the loading pattern that causes the maximum bending moment at this location. Similarly, you can generate the plots not only just for bending moment but also for other load effects. It can be axial forces, shear forces, and what we say that out of plane shear forces as well. The value is shown here. I can click write maximum to a file and then click OK, and again this kind of sheet is generated. So what I'll do now is, having this load applied to the structure, I'll convert this load into a static load and apply it back onto the structure as point loads. So for this I'll go to tools, MCT command shell, and then just open the two files which were just recently created, which is 161. I'll click open, hit run. It'll ask me whether you want to erase all your results. I'll say yes, and the moment I do that, you can see here a new load case is generated with the name MVL, MVmax, MXX 161, that is corresponding to element 161, and then I hit clear and then open, repeat this for the other set of loading, which is right here. 855, click open and then hit run. So you can see another load case generated, and then I can display this loading onto the structure by right click and select display. So you can see the loading has been applied onto the structure by converting it into static load, and I can use this to obtain any kind of concurrent forces I want. Let me undisplay this and let me rerun this analysis, and I can afford to do that because the analysis time is less than half a minute. And you can see the analysis being run. And the analysis is completed now, and now let's say you being engineers, and of course we need to design this slab, so we want the equivalent forces. We don't care about the forces per unit foot or stress values that are out there. We want to extract what forces are there at a particular cross section for me to go ahead and design this member. So what you can do is, for this type of need, we have a feature called local direction force sum, which is located under result. You can click on this and set the, let's say the tolerance as 1 here, and you can click on the position, let's say at this location. Click here, click at the other extreme, and then at, I'll just turn right and make another cut there, and then click calculate. Oops, I think I missed the nodes here. Let me try it one more time. Click here, go right across. Yeah, so when I click calculate, you can see the axis shown and the values shown from the stress values that were there. So you can see, if I let me zoom in at this location and rotate the structure in such a manner, so you can see X, Y and Z. This is the local direction of this cut, and the value that you are seeing, this mx, is the bending moment about this axis, this local x. Mz is the bending moment about the local z axis that you can see here, and my will be the bending moment about the vertical axis at this location. So depending upon the direction of your cut, you can control the local axis direction, and here you can see the values. So this is the axial, fx, fy, fc, mx, my, mz, and the length of the cut was this one. So you can save this location. Let's say it is at, this is location 1, x equal to 34, or you can save it with the name, let's say location 1, and then you can click add. So the program remembers this locations for you. You can then go on and change the load and still generate on the same location what is the contribution of the other load cases onto this member, and you can have all the static load cases that are there to see the similar effects. So let's say we want to see the effect of the static load we just created from the live load onto this section, and I'll click calculate here, and the program generates this. These are the values for this load case at the particular location. So you can just go on changing the load cases here. You can choose to select all load cases and combinations, so the program will generate a text file for this particular location and for all load cases and combinations and generate the values, and then you can choose to create a text output like this in no time. So it will show you at, because of this load case, this is the value. For this load case, this will be the value, and so on and so forth. So you can select your critical sections, cut across that plane, and let the program calculate the design forces for you in no time. And once you have these design forces, you can go ahead and use any kind of design tool that you prefer, like spreadsheets or your own set of written MathCAD programs to quickly get the design done. So this covers the third point that I was saying, that how easy the result extraction can get. And let me show you some more locations to generate this kind of results. So let's say I want to have another set of result at along the longitudinal axis, and then I'll click calculate, and for this axis this is the value for the given load case. I can choose this location as location 2 and then click add. And now for both these two, I can just choose to create a text output for all load case combinations, and the program will generate it for me. So just like this. Let me close this, and if you want to generate the text output for just individual load cases at individual locations, you can select them and click text output, and the program will write you a third file which will show you that due to this load given load case that you choose, at location 2 the value is this much, at location 1 the value is this much, and you can go ahead. But the point to be noted is that you should maintain the consistency of your cut, so that you have you need not go back and see at different locations what is the axis direction, so that you can interpret the results correctly. So with this I'll move, this is what I wish to explain with for the box culverts, how to extract the results using finite elements through the approach of local direction foursome and cutting plane diagrams. So as you can see here, result extraction is as simple as just cutting or drawing lines and hitting buttons and generating the text output in no times. Now I'll move on to the second portion of the webinar, which we will be talking about an integral abutment bridge, which will look like this. We'll have the pile members, we'll have the abutment wall, still have a wing wall, it will have girders underneath it, the intermediate diaphragms, and the deck of course on top of it. So again we'll be defining the material properties, and then nodes and elements will be created, static loads, live loads, everything will be done using the RC frame wizard. Now once the model is generated, you can go in and modify and make the model or customize the model to suit your field requirements. Like you can set what type of beams you want to use and what kind of pile elements you are using, so you can provide them spacing and create them in no time. Then you can use the auto generation tools for generating soil springs for integral abutments as well as for pile, and then move on for analysis and result extraction. So this is how our bridge looks like. This bridge we have used is in SI units, so it is 36 meter long, 6 meter is the wing wall dimensions, and this is the cross section of the bridge, and this is the wing wall dimensions. 1.132 is at this end, and as I mentioned, it is 6 meters long and 5 meters deep is the wing wall, and underneath that we have the pile members excuse me, which is like 20 meter deep. So I'll go back into the program now and create this in no time. So I'll start with a new, I'll click no to save changes with a new file here, and just to save some time, instead of going and defining the materials and sections again and again, what I'll do is I can either right click, go to properties, go to material, and import the material from a relevant project. So let me just go to a file and select webinar, and here under box culvert, let's say this is the model file I want to bring in the material properties from integral bridge material section. So I'll just click open, and the program will show this kind of dialog box popping up, which will have concrete and steel material, for steel for piles and concrete for the rest of the bridge. I'll click OK to that, and the moment I do that, the program has brought in the information from that model file into this model file. So it's as simple as recycling your material properties. So if you have one set of material property that you use frequently, you can create your own library, and every time you need not go and define those materials, you can directly pick them up from that library file, again saving on time and increasing the efficiency. Now I click close and go to model, structure wizard, and come back to the same wizard, that is reinforced frame and box culvert. And this time I'll and use a normal type frame and enter the dimensions. Since it's a single span bridge, I'll just enter the dimensions for single span and everything. To save some time, I have saved the wizard file, which I'll just open from here, integral abutment wizard file, and as you can see, the dimensions are given here. In order for the dimensions to be similar to the drawings that we have here, I'll close the dialog box, switch the unit system to kilonewton and meter, and then I'll go back to model, structure wizard, reinforced concrete frame, and then open the wizard file that I had. And now you can see the span length is 36 meters, the thickness of the wall, wing wall is 0.6, the plate element size I have taken as unit dimension, and other parameters have been entered just by looking at the bitmap image. Now you can come to the transverse tab, and here you can see the dimensions for the bridge have been given. The carriageway is given as 6.4 meter wide, then 1.5 meter is the sidewalk, and the barrier dimensions are given here. And since we'll have it's a frame bridge, so we don't have to enter the spring supports right here, because we'll be having the piles and integral abutment supports later. Then you have the loads tab. Here again we have the load combinations that will be generated as per H2 LRFT. The live load will be generated as per H2 LRFT. Click OK, and there you can choose the other settings. So in this since it's not a box culvert, the underground water level is not taken into account here. We don't have a sidewalk here, it's a pavement there. I mean, we are not considering the loading there, but you can choose to pick and choose any set of loading as shown in the previous example. And once we have entered all these values, I'll just go ahead and click OK, and the program will generate this kind of frame, which will have the abutment wall, the wing wall, and the deck on top. And now we are supposed to just create the girders and the piles based on the spacing and dimensions we want to do. So let me just turn off the nodes for the time being, so that the view is more clearer and it becomes easier for me to transmit it over the internet. And I have a question from Daniel. He asks why D is always set to 6 meters. It's not a default, or I mean, it's just a default value. You can choose whatever dimensions you feel is appropriate. D doesn't always need to be 6 meters. It can be any value that is here. So basically the things that are grayed out, you can ignore them. It's only the editable text fields that you can fiddle and play around with. So just ignore the values that are grayed out. And this is a good aspect of the software, that it shows you only the relevant bits of information. So if you have no idea what D is, or why it is 6 or less than 6, whatever the case be. uh, you can just hit F1 from the keyboard and it will open the Internet Explorer. uh, and will bring up the field relevant to this bit of information. Daniel, does this answer your question? As you can see here, pops up, and here you can see all the details about different inputs that are there. What does each input mean? So you can see B1, B2 and D is that the dimensions that guide the cross-section area, transverse area. And so basically you can read through this entire literature, and you can um, understand the dialog box inputs. And if you have any questions, then we are here to help you out with it. Let me close this. Um, there is another user, Abu Farah. He wants to know that how to regenerate the model file from the wizard once it is created. So if you have saved your wizard file once, then you can always open the wizard file in the program itself and then hit OK to generate it. But if you already have the model file at the same location and then you again go ahead and click OK, it will overlap at the same location. And if you don't want that to happen, what you can do is if the last step was, or if you have recently created the model file, you can just hit undo and then modify, make changes in the wizard and then hit OK. The program will generate the model from scratch, so it will overlap the image overlap the data, that is overlap the elements that are already there. So in order to avoid any kind of overlap, it is advisable that you just hit undo or get rid of your geometry and then click open and then make changes and then click OK. And yes, Abu, the wizard can be saved anywhere in the location. It need not be in the same folder or the directory. So the wizard file is not created every time. You can save it with different names at different locations, and then under relevant scenario you can bring them up and open it. Alright, so moving on with the geometry that is generated here, I'll quickly create the girders underneath and the diaphragms. So I'll right click, go to elements, create elements, and select the grade of concrete and the actually these sections are not here because we just imported the material properties. So what I'll do is open the different model file which has the material sections defined, just to save some time here. Let me open the file, open materials section file, click no to save changes. So you can see we have the sections defined here, where one H pile section, intermediate diaphragm, and the bulb T that we'll be using. You can right click, go into the properties and see the dimensions here. And let me just go back to model, structure wizard, reinforced concrete frame, and box culvert. I'll open the wizard file, click open, and then select the live load as per ASHTO LRFT. Click OK, and then click OK again, and the program will generate the bridge in no time. Now let me just hide the nodes for the time being and go ahead and create the elements. So elements, create elements. I'll select the grade of concrete, the bulb T beam, and then I'll go ahead, let me switch to a wireframe geometry so that it's more visible. I'll click on nodal connectivity, and I on purpose control the spacing of the plate members in such a manner that I get the node at the exact location or very closely at the very location where you can create the girders. So I'll click on this node and then go all the way across, click at the other end to create the girders. So then I'll just jump one block, come here and create the next one. And then I'll jump one more block, come here and go for the next one. And then from here I'll have an element right here. And then jump one block, come here and then have the other end of the element. So in this way we have created some elements, and now I'll go to the top view and create the diaphragm. So I'll switch the element from bulb T to diaphragm, and diaphragm divides this 36 meter bridge into 3 parts, 12, 12 and 12. So I'll just move across the bridge and see the location where I'll get 12. So you see here at the status bar at the bottom of the screen you can see X is 12. So I'll click from here, go all the way across and have the diaphragm connected to the other end of the girder. Same thing, I'll just move on and find 24, 23, 24 here. The X coordinate is 24 from here. Click on this node and then go there and click on the other node. And then I'll click close here and turn on the solid view so that you can see the girders that are created underneath. You can see the girders there and the diaphragms in between. I can choose to just double click on girders so you can see the girders are right there. Basically due to the same color they are shown with difficult to sight or when it is being webcast. So the geometry is ready. Now I'll quickly create the piles underneath the structure. So let me switch to a wireframe geometry and unselect everything, and using single select I'll just select the nodes where I want to have my my pile elements, and I'll have pile elements at the given nodes as you can see here. Similarly at the other end of the bridge. So I'll have the pile elements right there, and then I'll right click, go to the elements, extrude them, steel material with H pile, and the distance will be equal distance and -2 meter, and repeat it 10 times. Then click apply. So here you can see the piles are generated, and if I switch to the solid geometry you can see the pile members right there. The bridge is ready, and now we'll apply the boundary conditions. Loading is already there, so we'll start by applying the integral abutment soil springs. To start with, what I'll do is select the face of the abutment on which I want to apply the springs, which is 1.2 meter thick. So I'll just double click and you can see the members are selected. Let me right click and go to the boundaries, and in the boundaries we have a special type of spring support system, as you can see, which is integral bridge spring support. And then I'll click on this particular spring support. I'll choose that I want to apply abutment springs. And if you look at this bitmap image, it will show you two kinds of springs. One is blue color spring and one is red color spring. Blue color spring represents the plane condition. So they will be the non-linear springs in the in the plane, and then we have point spring at the base. If you want to have a raft foundation underneath, you can choose to have this kind of spring conditions at the for raft foundations. But since we have piles underneath this abutment, so I'll ignore the red springs. So I'll just select the elements that I've already selected. I'll not have any footing at this point, and my abutment height, as we know, is 5 meters. The thickness of the abutment wall is 1.2 meters, and the deck length in the transverse direction is 10.36 meters. And then the void ratio for this soil property is, let's say, 0.8. The specific gravity is 2.65. So you can enter your soil parameters here. You can enter the thermal expansion that you want to have, the coefficient of thermal expansion can be selected based on the material property that you have defined. And here you can enter the differential deck temperature. So for here we'll have this delta T as 5 degrees, and since we don't have any strip footing for now, I'll just leave this set of box as empty. Then I'll click apply, and the moment I do that, you can see the springs are generated on the surface of the abutment. And then I can click close here, so you can see all the compression tension only springs have been generated at the surface, which are equal to 156 in number. Then I'll select all the pile members by clicking on HP pile section. I'll right click, go to the boundaries and integral bridge spring support, and here I'll select the pile springs. And if you see, again we have the arrangement of red and blue springs. Blue spring will replicate the soil conditions in that plane. It can be which will show you the non-linear or multilinear springs, whereas the red spring is a linear spring along the surface of the pile that will behave as gives you the skin friction for that pile. So you can select different soil properties, soil types that you have. You can select the layers of pile elements. Let's say if the sandy soil is from the top of the pile to, let's say, 1/3 of the length, you can select only those pile elements, have this material property, and click apply. If you want to have second layer, you can choose the second layer of the pile elements, modify the soil parameters, and then click apply. And in this manner you can have a layered soil structure. But for the time being and just for the purpose of demo, I'm using a same layer soil throughout. The ground level is at 0 meters, that is the deck elevation. Then the 0 here. Then the diameter of the pile is H pile, so I'll use the diameter as equal to its total height of the section in the cross section, which is 0.312 meters. And this is the unit weight of the soil. Coefficient of earth pressure at rest, you can enter it here. Then you can enter the subgrade reaction of the soil, which is 13,000, and you can enter the internal friction angle. All these parameters are user defined, so if you happen to have different set of soils or different conditions, you can modify these parameters, and then you can choose what is your initial soil modulus, if it's dense, loose, medium, or none. Or if you choose none, then you can modify this parameter yourself. But for the timing, we'll stick to dense sand, and then click apply. The moment you do that, you can see the springs are generated at the surface all through the depth of the piles. Then I'll click close here, and now you'll see a set of linear piles and again set of multilinear piles that are generated. If you want to see their properties, you can just right click, go to their properties. You can see individual springs in this manner. You can right click and go to their tables and see the multilinear springs and their properties as shown here. And again, to make it more legible, I'll just right click, go to sorting dialog, select the type of supports, set the priority as top, and then click close. So you can see compression only values, you can see the stiffness values that are entered by the program, then the tension only, and the multilinear soil springs, which are generated just based on your crude boring log data. So if you happen to have all the set of data with you, you can enter the soil parameters yourself. For that, you can use right click, boundaries, and go to point spring supports and choose what kind of soil spring you want to have: linear, compression only, tension only, or multilinear. And depending upon what kind of values you have, you can choose what kind of springs you want to use and enter that data. So if you get the values from geotechnical engineers, fair enough, you can come and define your own set of springs. If you want to use the program's auto-generated springs, you can use that. If you want to compare the results, you can choose that approach also, or you can go in and modify the values. Basically, let's say you see that the for some reason at the base of the pile some spring conditions or soil conditions cannot be replicated in the program. So what you can do is enter those spring data from your own set of spring coefficients. So you can see how flexible the program is. It fluctuates from completely program or auto generation feature to a completely user defined format. So you can take controls in your hand, and you can go to whatever extent you want in this software. The program also generated based on the wizard some fixed support at the base of the abutment wall. We don't need them, so I'll just click on them and hit delete from the keyboard. So we are now left with only soil springs that will support the entire structure. Now we are good to perform analysis. So what I'll do is click perform analysis and see the analysis being performed right here. And I realize we are about to go just over the time limit, so I'll be real quick now. Or let me open the model file with the analysis already done, so that way I can save some time. So let me bring up the model file with integral supports in there. Let me open as a separate file. Oh, but before I could open the file, the analysis itself is completed. So let me just proceed with some results for pile elements. So what I'll do is right click, go to the displacement contours, and just for one set of loading I'll choose deform shape, legend, and click display. So you can see the displacement that is there. You can see the values and the magnitudes given here. So it's about 2.6 centimeters, which is close to an inch. So you can see that by the way, I didn't apply any pretension in this in these girders, so you can see the displacements will be higher. So once the precessing strands are there, then you can have more realistic image of it. But my concern for this example was to show you the pile elements and their behavior under these loadings. So let me activate the pile elements only, so that you can see the deformations that are occurring. And as you see towards the bottom of the file, the displacements are negligible. And let me show you some bending moment diagrams for the pile elements. You can select let's say for the dead loads, because they become really easy to comprehend. Solid fill, and let's say FX. So here you can see the axial forces are maximum at the top, and they go on decreasing as you move down the length of the pile. So the pile behavior is correctly replicated in the software, and you can also choose a bending moment about major axis and then see the bending moment distribution. So here you can see the at the top of the pile the bending moments are coming, and then they are like dying out because of the soil condition and the spring that have been simulated here. So in this way you can obtain the pile results in no time. And let me now show you, let me activate the entire structure. So just looking at the beam results, you can see a good amount of negative moment at the two integral abutments at that location. You get a nice bending moment diagram right there. And if you want to see the forces in the plate elements in the abutments, so what you can do is go switch to plate forces and moments, and then click apply, and the program will show you the contour plots. You can choose to have average nodal for display, and you can see right at the locations where the beam members are located, the stress concentration is higher, obviously because the load is being transferred and it is behaving as integral at this ends. And you can simulate the loading for different load cases and different load combinations, as you can see from here. Alright, so this was all I wanted to show it to you. Here you can see how we used plate elements and beam elements in conjunction with each other in the same model file, and able to extract results and interpret them. And we can use soil springs to generate and analyze pile, and these soil springs are automatically generated from crude boring log data. So thus the program is able to handle the integral abutments. Geometry is no limitation, boundary conditions are no limitation, analysis speed is no limitation, and result extraction is fairly simple, as you just saw in this webinar. So if you have any questions or comments for me, you can speak to us directly. You can have my contact details as shown on the screen. We look forward for your questions and comments on this webinar. Feel free to mail me all your questions and we'll get back to you as soon as we can. I'm sorry I'm not able to take all the questions in this session today because of the time constraints and the number of attendees and the number of questions. So I'll be answering to the questions which I couldn't answer right now through emails individually. Once again, thank you for joining us, and we'll look forward to see you tomorrow in the session where we'll be covering a curved steel girder composite bridge. Thank you.